Services within modular networks. Businesses that operate large enterprise networks strive to create an enterprise-wide network infrastructure and interactive services to serve as a solid foundation for business and collaborative applications. This section explores some of the interactive services with respect to the modules that form the Cisco Enterprise architecture. So the key point here is a network service is a supporting and necessary service, but not an ultimate solution. For example, security and quality of service are not ultimate goals for a network. They are necessary to enable other services and applications and are therefore classified as network services. However, IP telephony might be an ultimate goal of a network and is therefore a network application or solution rather than a service. So, interactive services, since the inception of a packet-based communication, networks have always offered a forwarding service. Forwarding is the fundamental activity within the internetwork. In IP, this forwarding service was built on the assumption that end nodes in the network were intelligent and that the network core did not have intelligence. So with advances in networking software and hardware, the network can offer an increasingly rich intelligent set of mechanisms for forwarding information. Interactive services add intelligence to the network infrastructure beyond simply moving a datagram between 2 points. For example, through intelligent network classification, the network distinguishes and identifies traffic based on application content and context. Advanced network services use the traffic classification to regulate performance, ensure security, facilitate delivery, and improve manageability. Network applications such as IP telephony support the entire enterprise network environment, from the teleworker to the campus to the data center. So these applications are enabled by critical network services and provide a common set of capabilities to support the application's network-wide requirements, including security, high availability, reliability, flexibility, responsiveness, and compliancy. Examining the role of the infrastructure services. Recall the layers of the Cisco SONA framework illustrated in the figure. So the SONA Interactive Services layer includes both application networking and the infrastructure services. So for example, the following infrastructure services shown earlier in the figure enhance classic network functions to support today's application environment by mapping the application's requirements to the resources that they require from the network. So these are security services. It ensures that all aspects of the network are secure, from devices connecting to the network to secured transport to data theft prevention. You also have mobility services. It allows users to access network resources regardless of their physical location. You also have these storage services, okay? So which provide distributed and virtual storage across the infrastructure. You also have voice and collaboration services. It delivers the foundation by which voice can be carried across the network, such as security and high availability. You also have this compute services. It connects and virtualizes compute resources based on the application. And you've got the identity services, which map resources and policies to the user and the device. Now, what are the reasons for internal security? Strongly protecting the internal enterprise campus by including security functions in each individual element is important for the following reasons. So that would be if the security established at the enterprise edge fails, an unprotected enterprise campus is vulnerable. So deploying several layers of security increases the protection of the enterprise campus where the most strategic asset usually resides. So relying on physical security is not enough. So for example, as a visitor to the organization, a potential attacker could gain physical access to devices in the enterprise campus. Okay? Often, external access does not stop at the enterprise edge. So some applications require indirect external access to the enterprise campus. Okay? So strong security must protect access to these resources. Modularizing internal security. So examples of network services embedded in the infrastructure services includes the following. So first, you've got the network management. Okay? So it includes LAN management for advanced management of a multi-layer switches, routed WAN management for monitoring, traffic management, and access control to administer the routed infrastructure of a multi-service networks. Service management for managing and monitoring service level agreements or SLAs. And VPN security management for optimizing VPN performance and security administration. So high availability ensures end-to-end availability for services. So that includes clients and sessions. So implementation includes reliable, fault-tolerant network devices to automatically identify and overcome failures and resilient network technologies. So also, we need the quality of service. So manages the delay variation, or also known as the jitter, bandwidth availability, and packet loss parameters of a network to meet the diverse needs of voice, video, and data applications. So quality of service features provide value-added functionality such as network-based application recognition for classifying traffic on the application basis. So Cisco iOS IP SLAs, or the previously called the Service Assurance Agent, for an end-to-end quality of service measurements. So resource reservation protocol signaling for admission control and reservation of resources, and a variety of configurable queue insertion and servicing function. So you also have multicasting or IP multicasting. So it provides bandwidth conserving technology that reduces network traffic by delivering a single stream of information intended for many recipients throughout the transport network. So multicasting enables distribution of video conferencing, corporate communications, distance learning, software, and other applications. So multicast packets are replicated only as necessary by routers enabled with protocol-independent multicast and other supporting multicast protocols that result in the most efficient delivery of data to multiple receivers. So to support network applications efficiently, so deploy the underlying infrastructure services in some or all modules of the enterprise network as required. So these design elements can be replicated simply to other enterprise network modules as network changes. So as a result, modularization to small subsets of the overall network simplifies the network design and often reduces the network's cost and complexity. So the following are some of the recommended security practices in each of the module. So you've got at the building, okay? So for building access, access is controlled at the port level using data link layer information. Some examples are filtering based on media access control addresses and the IEEE 802.1x port authentication. Okay? Now on the building distribution, it performs filtering to keep unnecessary traffic from the campus core This packet filtering can be considered a security function because it does prevent some undesired access to other modules. So given that switches in the building distribution layer are typically multi-layer switches and are therefore layer 3 aware, this is the first place on the data path in which filtering based on the network layer information can be performed. Okay, so you also have the campus core layer. So this is a high-speed switching backbone and should be designed to switch packets as quickly as possible. So it should not perform any security functions because doing so would slow down the switching of packets. So next would be the server farm modules, which primary goal is to provide application services to end users and devices. So enterprises often overlook the server farm module from a security perspective. Okay, so given the high degree of access that most employees have to these servers, they often become the primary goal of internally originated attacks. So simply relying on the effective passwords does not provide a comprehensive attack mitigation strategy. So using a host-based and network-based IPS and IDSS, so private VLANs and access control, provides a much more comprehensive attack response. So for example, onboard IDS or IPS within the server farm multi-layer switches that inspects traffic flows. Okay, now the server farm module typically includes network management systems to securely manage all the devices and hosts within the enterprise architecture. So for example, syslog provides an important information on security violations and configuration changes by logging security-related events, authentication, authorization, and accounting, and so on. So an authentication, authorization, and accounting, or AAA, that is a security server, okay? So also works on a one-time password or OTP server. That is to provide a high level of security to all local and remote users. So AAA and OTP authentication reduces the likelihood of successful password attack. Let me give you some information about AAA, or the authentication, authorization, and accounting. So AAA is a crucial aspect of network security that should be considered during the network design. An AAA server handles the following. So first is authentication. With authentication, that pertains to who. Authentication checks the user's identity, typically through a username and password combination. The next A is authorization. This pertains to what? So after the user is authenticated, the AAA server dictates what activity the user is allowed to perform on the network. So the last A is accounting. Accounting pertains to when. The AAA server can record the length of the session, the services accessed during the session, and so on. So everything will be logged in on the accounting server. How about external threats? So when designing a network security in an enterprise network, the enterprise edge is the first line of defense at which potential outside attacks can be stopped. So the enterprise edge is like a wall with small doors and strong guards that efficiently control any access. So the following 4 attack methods are commonly used in attempts to compromise the integrity of the enterprise network from the outside. So first would be IP spoofing. Okay? So IP spoofing attack occurs when a hacker uses a trusted computer to launch an attack from inside or outside the network. The hacker uses either an IP address that is in the range of the network's trusted IP addresses or trusted external IP addresses that provides access to specified resources on the network. IP spoofing attack often lead to other types of attacks. For example, a hacker might launch a denial of service attack or DOS using spoofed source address to hide his identity. Okay? So you also have password attacks. So using a packet sniffer to determine username and passwords is a simple password attack. However, the term password attack usually referred to repeated brute force attempts to identify username and password information. So Trojan horse programs are another method that can be used to determine this information. So a hacker might also use IP spoofing as a first step in system attack by violating the trust relationship based on the source IP addresses. So first, however, the system would have to be configured to bypass password authentication so that only username is required. So you also have these DOS attacks or the denial of service attacks. So DOS attacks focus on making a service unavailable for normal use and are typically accomplished by exhausting some resource limitation on the network or within an operating system or applications. Okay, so also we have this application layer attack. So application layer attacks typically exploit well-known weaknesses in common software programs to gain access to a computer. Designing high availability. So most enterprise networks carry mission-critical information. Organizations that run such networks are usually interested in protecting the integrity of that information. Along with security, this organization expects the internetworking platform to offer sufficient level of resilience. So this section introduces another network infrastructure service, high availability, to ensure adequate connectivity for mission-critical applications. High availability is an essential component of an enterprise environment. Okay? Now, designing for high availability in a network. So redundant network design, duplicate network links and devices, eliminating single point of failure on the network. That is high availability. So the goal is to duplicate components whose failure could disable critical applications. So because redundancy is expensive to deploy and maintain, redundant topologies should be implemented with care. So redundancy adds complexity to the network topology and to network addressing and routing. So the level of redundancy should meet organizations' availability and affordability requirements. So what's the key point here? So before selecting redundant design solutions, analyze the business and technical goals and constraints to establish the required availability and affordability. So critical application systems, internetworking devices, and link must be identified. So analyze the risk tolerance and the consequences of not implementing redundancy, and ensure that you consider the trade-offs of redundancy versus cost and simplicity versus complexity. So duplicate any component whose failure could disable critical applications. And redundancy is not provided by simply duplicating all links. So unless all devices are completely fault tolerant, so redundant links should terminate at different devices. Otherwise, devices are not fault tolerant, becoming a single point of failure. How about designing for route redundancy? So the following types of redundancy may be used in the modules of an enterprise. So you've got sort of device redundancy, including card and port redundancy. You also have redundant physical connections to critical workstations and servers. Route redundancy can also be considered, link redundancy, and even power redundancy, including redundant power supplies integral to the network devices and redundant power to buildings' physical plant. Now, designing for redundancy. So redundant routes have two purposes. So that is to minimize the effect of link failures and to minimize the effect of the internetworking device failure. So redundant routes might also be used for load balancing when all routes are up. Okay? Now, possible ways to make connection redundant includes the following. So you've got parallel physical links between switches and routers. You could also have backup LAN and WAN links. For example, DDR backup for less lines. Now, the following are possible ways to make the network redundant. So a full mesh to provide complete redundancy and good performance. A partial mesh, which is less expensive and more scalable. The common approach when designing the route redundancy is to implement partial redundancy by using a partial mesh instead of a full mesh and backup links to alternative devices. So this protects only the most vital parts of the network, such as links between the layers and the concentration devices. Now, example of campus infrastructure redundancy. So a full mesh forms any-to-any connectivity and is ideal for connecting a reasonably small number of devices. However, as the network topology grows, the number of links required to maintain a full mesh increases exponentially. So the number of links in a full mesh is n, okay, times n minus 1 divided by 2. Okay, so where n is the number of routers. So as the number of router peer increases, the bandwidth and CPU resources devoted to processing routing updates and service requests also increases. Now, in a partial mesh network, that is similar to the full mesh network with some of its connections removed. Okay? Now, a partial mesh backbone might be appropriate for a campus network in which traffic predominantly goes into one centralized server farm module. Now, this figure here illustrates an example of route redundancy in a campus. Okay? Now, in this example, the access layer switches are fully meshed with the distribution layer switches. Okay? If the link or distribution switch fails, an access layer switch can still accommodate and communicate with the distribution layer. Now, the multi-layer switches select the primary and backup path between the access and distribution layers based on the link's metric as computed by the routing protocol algorithm in use. The best path is placed in the forwarding table, and in case of equal cost path, load sharing takes place. How about example of edge redundancy? So designing for link redundancy, it is often necessary to provision redundant media in locations where mission-critical application traffic travels. So in layer 2 switch networks, redundant links are permitted as long as STP is running. So STP guarantees one and only one active path within the broadcast domain, avoiding problems such as broadcast storms, when a broadcast storms continuously loops. Okay? Now, the redundant path automatically activates when the active path goes down. So because WAN links are often critical pieces of the internetwork, redundant media are often deployed in WAN environments. Now, if you will observe on this figure here, where frame relay circuit is used in parallel with backup IPsec connection over the internet. So backup links can use different technologies. And so with the frame relay, which I said from the previous video, is almost obsolete. Okay? Now, it is important that the backup provides sufficient capacity to meet the critical requirements if the primary route fails. So backup links can always be on or become active when a primary link goes down or becomes congested. So you have this connectivity. Okay? So one is active, the other one is standby. Now, how about high availability in the server farm module? So improving the reliability of critical workstations and servers usually depends on the hardware and operating system software in use. Some common ways of connecting includes the following. So you could have the single attachment, okay, so which is not recommended. So when a workstation on a server has traffic to send to a station that is not local, it must know the address of the router on each network segment. So if that router fails, the workstation or server needs a mechanism to discover an alternative router. So if the workstation or server has a single attachment, it needs layer 3 mechanism to dynamically find an alternative router. Therefore, the single attachment method is not recommended. Okay? So the available mechanism includes Address Resolution Protocol or the ARP. You've got Router Discovery Protocol or RDP, routing protocols such as Routing Information Protocol, RIP, OSPF, EIGRP. You could also have this Hot Standby Router Protocol, okay, or the HSRP, the Gateway Load Balancing Protocol, JLBP, and the Virtual Router Redundancy Protocol, VRRP. Now, example attachment through a redundant transceiver. Okay, so this is an attachment through redundant transceiver. So physical redundancy with redundant transceiver is suitable in environments where the workstation hardware or software does not support redundant attachment options. Okay. Now on this diagram here, it is an example of attachment through redundant NIC. Okay. So attachment through redundant network interface cards or NIC, some environments, for example, most Unix servers support redundant attachment through dual NICs. So primary and backup. So the device drivers represents this attachment as a single interface to the operating system. Now for fast Ethernet or Giga Ethernet port bundles, so fast Ether channel and Gigabit Ether channel port bundles group multiple fast or Gigabit Ethernet ports into a single logical transmission path between a switch and the router. So host or another switch. So STP treats the Ether channel as one logical link. So the switch distributes frame across the ports in an Ether channel. So this load balancing was originally done based only on MAC addresses. So however, newer implementations can also load balance based on IP addresses or layer 4 port numbers. So source, destination, or source and destination addresses or port numbers can be used. So if a port within an Ether channel fails, traffic previously carried over the failed port reverts to the remaining ports within the Ether channel. So if you want to learn more about Ether channel, you could go ahead and check the supplementary videos on Ether channel. Voice transport overview. So voice services in a modular network design. So to ensure successful implementation of voice applications, network designers must consider the enterprise services in infrastructure in each configuration. For example, to support VoIP, the underlying IP infrastructure must be functioning and robust. In other words, don't even think of adding voice to a network experiencing other problems such as congestion or network failures. Okay? Now, to voice implementations, voice transport is general term. So that can be divided into the following two implementations here. Okay? So you've got the VoIP or the voice over IP and the IP telephony. Now, VoIP uses voice-enabled routers to convert analog voice into IP packets or packetized digital voice channels and route those packets between the corresponding locations. Users do not often notice that VoIP is implemented in the network. So they use their traditional phones, which are connected to the PBX. However, the PBX is not connected to PSTN or to another PBX. Okay, so but to a voice-enabled router that is an entry point to VoIP. So voice-enabled routers can also terminate IP phones using session initiation protocol for call control and signaling. So the next one would be IP telephony. So for IP telephony, traditional phones are replaced with IP phones. So a single or a server for call, control, and signaling, such as this Cisco Unified Communication Manager. Okay, so the IP phone itself performs voice to IP conversion, and no voice-enabled routers are required within the enterprise network. However, if a congestion to the PSTN is required, a voice-enabled router or other gateway in the enterprise edge is added where calls are forwarded to the PSTN. So both implementation, VoIP and IP telephony, require properly designed networks. So using a modular approach in voice transport design, that is especially important because of the voice sensitivity to delay and the complexity of troubleshooting voice networks. So all Cisco Enterprise Architecture modules are involved in voice transport design. IP telephony components. So IP telephony components, an IP telephony network contains 4 main voice-specific components. Okay, so this includes an IP phones. Okay, an IP phone are used to place calls in an IP telephony network. They perform voice to IP and vice versa coding and compression using special hardware. So IP phones offer services such as directory lookup and internet access. So the phones are active network devices that require power to operate. So power is supplied through the LAN connection using the PoE or with external power supply. Okay, so the next one would be switches with inline power. So I've got switches there. So switches with inline power or PoE enable the modular wiring closet to provide centralized power for the telephony networks. So these switches are similar to traditional switches with an added option to provide power to the LAN ports where IP phones are connected. Now the switches also perform some basic QoS tasks such as packet classification, which is required for prioritizing voice through the network. So also, you have this voice or the call processing manager, okay, or the call processing engine. Now, the call processing manager, such as the Cisco Unified Communication Manager, it provides central call control and configuration management for IP phones. So it provides the core functionality to initialize IP telephony devices and to perform call setup and call routing throughout the network. Okay. Now, this Cisco Unified Communication Manager can be clustered to provide distributed, scalable, and highly available IP telephony model. So adding more servers to cluster of servers provides more capacity to the system. Okay. Next would be the voice gateway. Okay. So voice gateways, also called voice-enabled routers or voice-enabled switches, provide voice services such as voice to IP coding and compression. So PSTN access, IP packet routing, backup call processing, and voice services. So backup call processing allows voice gateways to take over call processing in case of the primary call processing manager fails. So voice gateways typically support a subset of a call processing functionality supported by this Unified Communication Manager. So other components of IP telephony network includes a robust IP network, of course. Okay, so voice messaging and applications, and a digital signal processor resources to process voice functions in hardware. So which is much faster than doing it in software. So these components are located throughout the enterprise network, as you can see here on this diagram. Modular approach in voice network design. So implementing voice requires deploying delay-sensitive services such as end-to-end in all enterprise network modules. So use the modular approach to simplify design, implementation, and especially troubleshooting. So voice implementation requires some modification to the existing enterprise network. Okay, so that is in terms of performance, capacity, and availability because it is an end-to-end solution. So for example, so clients' IP phones are located in the building access layer. Okay, and then the call processing manager is located in the server farm. Okay, so therefore, all modules in the enterprise network are involved in voice processing and must be adequately considered. Voice affects various modules of the network as follows. Now, on the building access layer, IP phones and end user computers are attached to a layer 2 switches here. So switches provides power to IP phones and provide quality of service packet classification and marking, which is essential for proper voice packet manipulation through the network. Okay, now on the building distribution layer, this layer performs packet reclassification if building access is unable to classify packets or is not within trusted boundary. So it aggregates the building access layer switches or the wiring closets and provides redundant uplifts to the campus core layer. Okay, now on the campus core layer, this forms the network's core. So all enterprise network modules are attached to it. However, okay, so this could be virtually all traffic between application servers and clients traverses the campus core. And with the advent of wire speed multi-layer gigabit switching devices, LAN backbones might have migrated to switch gigabit architectures that combine all the benefits of routing with wire speed packet forwarding. Okay, now on the server farm, so this module includes multi-layer switches with redundant connections to redundant Cisco Unified Communication Managers, which are essential for providing high availability and reliability. Now for the enterprise edge, okay, now the enterprise edge extends IP telephony from the enterprise campus to remove locations via WANs, okay, the PSTN or the public switch telephone network, okay, and the internet. Example voice network solution. So this figure here shows the voice network solution in the Cisco enterprise architecture. So it illustrates how a call is initiated on the IP phone, okay, so going to the destination. Okay, so how the call setup goes through the Cisco Unified Communication Managers and how the end-to-end session between the IP phones or the two IP phones is established. So take note that the Cisco Unified Communications Manager is involved in only the call setup. Okay, now calls destined for remote locations traverses the enterprise edge. That is through the WAN and MAN, and also, if possible, that could be via the site-to-site VPN module or through the remote access and VPN module. So calls destined for public phone numbers on the PSTN are routed over the enterprise edge through the remote access and VPN module. So calls between IP phones traverses the building access, the building distribution, okay, and the campus core layers, and of course, the server farm module. So although call setup uses these modules, speech employs only the building access, building distribution, and in some cases, the campus core layers. Evaluating the existing data infrastructure for voice design. So evaluating the existing data when designing IP telephony, designers must document and evaluate the existing data infrastructure in each enterprise module to help determine upgrade requirements. So items to consider includes the following. So first, of course, we have to talk about performance. Okay. Now, enhanced infrastructure for additional bandwidth, consistent performance, or higher availability if required might be necessary for the conveying or converging environment. Okay. Now, performance evaluation includes analyzing the network maps, device inventory information, and network baseline information. So links and devices such as with high peak or busy hours, okay, so use might have to provide sufficient capacity for the additional voice traffic. So devices with high CPU use, high backplane use, high memory use, queuing drops, or buffer misses might have to be upgraded. Okay, so the next one would be availability. Okay, so redundancy in all the network modules should be reviewed to ensure that the network can meet the recommended IP telephony availability goals with the current or new network design. Next would be the feature requirements. So examine the router and switch characteristics, including the chassis, module, and software version. That is to determine the IP telephony features, okay, in the existing environment. Next would be the potential network capacity or impact. Okay, so for the capacity, evaluate the overall network capacity and the impact of IP telephony on a module by module basis to ensure that the network meets capacity requirements and that there is no adverse impact on the existing network and application requirements. Now for power, assess the power requirements of the new network infrastructure, ensuring that the additional devices will not oversubscribe existing power. Consider taking advantage of the PoE capabilities in devices. How about wireless LAN? Okay, so wireless services in a modular network. So a wireless LAN or WLAN supports mobile clients connecting to the enterprise networks. The module clients do not have a physical connection to the network because wireless LANs replace the layer 1 traditional wired network, usually Cat5 or Cat5e. Okay, so with the radio frequency or RF transmissions through the air. Now, wireless LANs are for local networks, either in building, line of sight, outdoor bridging application, or combination of both. So in a wireless network, many issues can arise to prevent the radio frequency signal from reaching all parts of the facility, including multipath distortion, hidden node problems, interference from other wireless sources, and near-far issues. Now, a site survey helps find the regions where these issues occur by defining the contours of radio frequency coverage in a particular facility, discovering regions where multipath distortion can occur, areas where radio frequency interferences is high, and finding solutions to eliminate such issues. So privacy and security issues must also be considered in a wireless network. Okay? Because wireless LANs are typically connected to the wired network. So all the modules within the enterprise infrastructure must be considered to ensure the success of a wireless deployment. Centralized wireless LAN model components. So as illustrated on this figure here, the four main components in a centralized wireless LAN deployment are as follows. So first is basically you need the end user's devices. So a PC or other end user device in access layer uses wireless NIC to connect to an access point. Okay, so that is via radio waves. Next would be the access points or wireless APs. APs or access points typically in the access layer are shared devices that function similar to a hub. So the Cisco APs can either lightweight or autonomous. Lightweight APs are used in centralized wireless LAN deployments. A lightweight AP receives control and configuration from the wireless LAN controller, or the WLC, with which it is associated, providing a centralized point of management and reducing the security concern of stolen access point. So an autonomous AP has a local configuration and requires local management, which might make consistent configurations difficult and to the cost of network management. Of course, that would be added. Okay, so next would be the WLC, or the wireless LAN controller. A WLC provides management and support for wireless services such as roaming. The WLC is typically in the core layer of an enterprise network. And of course, you have to consider the existing switched and routed wired networks. So the wireless APs connect to the wired enterprise network. So if you want to learn more about these wireless LAN concepts and implementation, you could go ahead and check the supplementary videos. Application networking services. Okay. Now, traditional networks handled static web pages, email, and routine client-server traffic. So today, enterprise networks must handle more sophisticated types of network applications that include voice and video. So examples includes voice transport, video conferencing, online learning, online training, and audio and video broadcasts. So applications place increasing demands on IT infrastructure as they evolve into a highly visible services that represent the face of the business to internal and external audiences. Now, the large amount of variety of data requires that the modern network be application aware. Okay? So, in other words, be aware of the content carried across it to optimally handle that content. Now, it is no longer enough simply to add more bandwidth as needs grow. Okay? So networks have had to become smarter. A new role of emerging for the network as provider of application infrastructure services that extend the value of applications. Now, either by improving delivery of content to users and other applications or by offloading infrastructure functions that today burden development and operation teams. So application networking services, or ANS, provides this intelligence. Okay? All right. So ANS can resolve application issues. Okay? So for example, say we have the consolidation of data centers result in remote employees having slower access to centrally managed applications. So the sample ANS solution is basically wide area application services can compress, cache, and optimize content for remote users so that they experience a LAN-like responsiveness. Okay? So another sample deployment issue would be a new website or a new web-based ordering system experiences a high proportion of abandoned orders because of poor responsiveness during the checkout process. So the sample ANS solution would be optimization of the web streams being sent to an e-commerce portal, which reduces latency, suppresses unnecessary reloading of web objects, and offloads low-level tasks from the web server. Okay, so what else? Say you have a business partners need immediate, and secure electronic access to information held in the back office applications, such as shipment information. So the solution, might be security and remote connectivity services that automatically validates a partner's request, route it to the appropriate back office application, and encrypt and prioritize the response. Okay. Now, last one would be sample deployment issue. Purchasing application needs to log and track orders over a certain value of compliance purposes. So the AND solution would be application messaging service that intercepts purchase orders, locates the value, and logs large orders to a database according to business policy rules. Okay, so that's how ANDs can resolve application issues. Now, what are the ANDs components? Now, this figure here illustrates an example of ANDs deployed in offices connected over a wide area network, providing a LAN-like performance to users in the branch, regional, and remote offices. So ANDs components are deployed symmetrically in the data center and distant offices. The ANDs components in this example are as follows. So basically, they've got this wide application services, or WAAS. Okay, that is a software. So the Cisco WAAS software gives remote offices LAN-like access to centrally hosted applications, servers, storage, and multimedia. Okay, so another component would be this wide area application engine, okay, or WAE appliance. Now, the Cisco WAE appliance provide a high performance global LAN like access to enterprise applications and data. Now, the WAEs use either WAS or WAAS or the Application and Content Networking System, or the ACNS software. Now, the WAEs help consolidate storage, servers, and so forth in the corporate data center with only low-cost, easy-to-maintain network appliances in distant offices. Okay? Next would be Series Content Engine Module. Okay? Now, the Content Engine modules can be deployed in a data center or branch offices to optimize LAN and WAN bandwidth. So accelerate deployment of mission-critical web applications, add web content security, and deliver live and on-demand business videos. Now, to summarize, okay, so network infrastructure services add intelligence to the network infrastructure, supporting application awareness within the network. So security is a network infrastructure service that increases the integrity of the network by protecting network resources and users from internal and external threats. High availability services protect the integrity of mission-critical information with networking platforms and topologies that offer sufficient level of resiliency. Voice infrastructure services throughout the enterprise are needed to support IP telephony. So wireless services support mobile clients and integrate it with a wired network. And last would be the Cisco ANS or ANS optimizes website performance, content delivery, and the security and connectivity applications.